Hello, everyone, and welcome to Scale Models Lesson 3. You think I would start to do this beforehand? Scale models. I'll do it on the next one. Lesson number 3. So we have been looking a lot at linear scale factors, and we even looked at perimeter scale factors. Basically, linear scale factor is any linear measurement. So like a width is a linear measurement, a length, because it's one dimension. Perimeter, we looked at radius of a circle, even the diameter. But we can also look at area scale factor. So we know area is a two-dimensional, so this is one-dimensional. Two-dimensional measurements are areas, right? So if you have a rectangle, for example, you would do the area of that rectangle. Let's say it's a 2 by 3. The area is length times width. Hopefully you remember that. The area of a rectangle is length times width. So you would say 2 times 3, and the area is 6. So if this is 2 centimeters and 3 centimeters, the area is 6 centimeters squared because it's centimeters times centimeters, right? And that's a two-dimensional measurement. So the 2 centimeters here is a one-dimensional measurement. It's linear because it just measures that distance or that length, and that 3 only measures that one. But our area is two-dimensional. It measures how much this covers here. Hopefully that makes sense. So there is a link between area scale factor and linear scale factor, but they're not the same. So let's dive into this chart and we will talk about that. We'll kind of explore this a little bit. So let's skip over A and let's do B together. So it says here we have a rectangle, a 9 by 6 rectangle. Sometimes it's nice to draw a picture. A 9 by 6 rectangle. And they want to know the area. So we know area is going to be length times width. So we will get 9 times 6, and that gives us 54 centimeters squared. So the area of that is 54 centimeters squared. In the next column, we are going to apply a linear scale factor. That means we are going to change the dimensions. Those ones. We're not going to touch the area yet. The area is going to change because we changed the dimensions, but anything that's a dimension is one dimension, is a linear measurement. So we are going to apply 1/3 scale factor to each of those. So 9 multiplied by 1/3 is going to be 3, and 6 multiplied by 1/3 is going to be 2. So our new rectangle is a 3 by 2. And it makes sense that it's smaller than the original because our scale factor is less than 1. So we can calculate the new area of that rectangle. It's a 3 by 2. It's a little bit smaller. So it's a 3 by 2. And we know area is going to be 3 times 2, which is 6. Actually, I just did that over on the other side. So our new area is 6 centimeters squared. So just like linear scale factor, do you remember our linear scale factor was new over original? Well, now our area scale factor is just going to be new area over original area. So it's the same thing. It's the same formula, but now everything's an area, which is totally fine. So we'll do the same formula. New area over original area, 6 over 54, and that can be reduced to 1 over 9. So our linear scale factor was, let me erase this here. Our linear scale factor was 1/3, and our area scale factor was 1/9. In the example above, our linear scale factor was 2, and our area scale factor was 4. So we're kind of looking for a relationship here, some sort of link because it's going to help us in the future. So let's do one more. So we have a rectangle, a 4 by 8 rectangle. And if we want to find the area of that, we're going to just simply do 4 times 8 because it's length times width. And that gives us an area of 32 centimeters squared. Now we are going to apply a linear scale factor to the linear dimensions. So we are going to enlarge this rectangle because our scale factor is 3/2, which is bigger than 1. So our original rectangle is going to get bigger. So again, we'll just multiply 4. Maybe I'll do it over here on the side. 4 multiplied by 3/2 and 8 multiplied by 3/2. And when we do 4 multiplied by 3/2, we get 6, and 8 multiplied by 3/2 gives us 12. So our new dimensions are a 6 by 12. And so we can calculate the area of our new rectangle if we just do length times width, which is 6 times 12. And that gives us a new area of 72 centimeters squared. So remember, the whole exercise here is to compare our linear scale factor to our area scale factor. So we have our linear scale factor, 3/2. What is our area scale factor going to be? Well, we can calculate that by saying our new area, 72, divided by our original area, 32. And we can reduce that fraction. We can divide both top and bottom by 8. And we are left with 9/4. So now we have to ask ourselves, what is the link between, let's scroll a little bit. I'll use the margin here. Maybe I will erase this quick just so we have some space. So we are looking for a link between linear scale factor and area scale factor. So in our above examples, we had a linear scale factor of 2 and an area scale factor of 4. And a linear scale factor of 1/3 and an area scale factor of 1/9, and then a linear scale factor of 3/2 and an area scale factor of 9/4. So how can we link these two? And I will give you the answer right now. Unless you want to stop and think about it, then pause the video and have a think. But if not, I will tell you that if you square the linear scale factor, you will get the area scale factor. So if you square a fraction, let's write this over here more, 1/3. What's going to happen is if you square the whole thing, it's like squaring the top, 1 squared over 3 squared. Well, 1 squared, 1 times 1 is 1, and 3 times 3 is 9. So if we square this one, 3 squared is 9, 2 squared is 4. So you can say that right here, the area scale factor is equal to the linear scale factor squared. I also like to write underneath or somewhere else that I can erase this as well. So you can go the opposite way as well. You can also say, or the square root of the area scale factor is equal to the linear scale factor. So if you had the area scale factor and you wanted to convert that into a linear scale factor, you would just square root it. It's the opposite of square. All right, let's do a couple practice problems, but I'm not going to keep you here for too long. So it says here, Maggie has scanned an 8-inch by 10-inch photograph to her computer. Maggie would like to increase the size by 44%, and they say here they want to increase the size or the area by 44%. Determine the area scale factor and the linear scale factor. Okay, well, the original size of the photograph, we would say, is 100%. Everything is 100% of its size, right? And if we want to increase it by 44%, that means we want a new area of 144%. That's our area scale factor as a percentage. We want to convert that into a decimal. So just for future reference, 1.00 is 100%. 1.50 is 150%. And 0.50 is 50%. Hopefully you remember this, but if you don't, all you're doing is moving your decimal place over 2, or if you're going the opposite way, you would move your decimal place to the right by 2 to get 50%. So in this case, if we have 144% and we want it as a decimal, we would say 1.44. That's the area scale factor as a decimal. So if that's our area scale factor, we want to find the linear scale factor as well. Well, I know that in order to find the linear scale factor, I take the square root of the area scale factor. So I will take the square root of 1.44, and I know that the linear scale factor is 1.2 if I type that in my calculator. So now I found the area scale factor and the linear scale factor. And why are they different? Well, they're different types of measurements, right? Area is a two-dimensional measurement, and linear measurements are one-dimensional. So you could say that the area scale factor is the square of the linear scale factor. So determine the dimensions of the enlarged photo. So you gotta be really careful here. The dimensions mean the length and the width, which are they one-dimensional measurements or two-dimensional measurements? That's right. Length and width are one-dimensional, right? We have 8-inch by 10-inch. Those are 1-inch, or those are one-dimensional measurements, the height and the width. So the new dimensions are going to be, well, if we're doing one-dimensional measurements, we want to use our linear scale factor. So we can say, well, wait, hang on, before we go there, let's talk about so we know that we're looking for the dimensions of the enlarged photo, which is the new, and we know our formulas. I'll just write them here. Scale factor is new over original. Original is new over scale factor. And new is scale factor multiplied by original. So we are looking for new dimensions. So we're just going to go scale factor multiplied by the original. So we can say 8 multiplied by our linear scale factor is 1.2. So that we get 9.6 inches, and we're going to do 10 multiplied by 1.2, and that gets us 12 inches. So the new dimensions are 9.6 by 12. And those are the dimensions we need if we want to increase the area by 44%. The enlarged photograph will be printed at a digital print shop on a color printer. Assuming the white areas of the photograph will also use ink, calculate the area the printer must cover by the following two methods. Use the dimensions of the enlargement. Okay, so we're looking for the new area. So calculate the area. So we know the new dimensions, and we know area is length times width. So we can just say 9.6 multiplied by 12. And we get 115.2. That's inches times inches. So we are going to get inches squared. We can use the original area and multiply it by the area scale factor. So these are just two different methods, right? We know the original area is going to be, well, area is length times width, which gives me 80 inches squared. And I know my area scale factor is 1.44. So now I can go We're looking for the new area, so I can go scale factor multiplied by original area. So the new area will equal 1.44 multiplied by 80. And when we do that, we get 115.2 inches squared. So you can see it's the same answer. Whether you use the new dimensions to calculate the area, or you find the area scale factor and then just convert the original area to the new area. Either way is going to work. I'm going to do one more practice problem and then we're done this. We're not going to do this one. So it says here, oh, it's the same. Okay, it continues on from our last problem. Maggie must also produce a print whose area will be reduced by 25%. Determine the dimensions of the print to the nearest hundredth of an inch. So we're trying to find the, not the height, sorry, the length and the width. Dimensions mean the length and the width. And you got to be careful with the wording here. Reduced by 25% and reduced to 25%. So reduced to 25% means that our area scale factor is going to be 0.25. Reduced by 25% means that, well, we start always at 100% and we want to reduce that by 25%. So we would subtract 25% and that would give us an area scale factor of 75% or 0.75. So you got to be careful with the wording. Reduced by 25%. So that means our area scale factor, oh, my pen, I apologize, is going to be 0.75. But if we're looking at dimensions, which are one-dimensional measurements, do we want to use the area scale factor or should we try to find the linear scale factor? Correct, we want to use the linear scale factor. Luckily, we know that the linear scale factor is equal to the square root of the area scale factor. So if the area scale factor is 0.75, then the linear scale factor is the square root of 0.75. And I'll just leave that like that. You can calculate that. It's going to be a decimal that goes on forever, but we'll leave it as 0.75. So the original dimensions are 8 by 10, and we're trying to find the new dimensions. So something by something. So if we're looking for new, we know that new is equal to scale factor multiplied by original. So we can say, well, 8 is our original multiplied by the square root of 0.75, and that leaves us with what? 6.93 inches. And 10 multiplied by the square root of 75, and that gives us 8.66 inches. So our new dimensions are 6.93 by 8.66 if we want to reduce the area by 25%. Okay, hopefully that made sense. We're not going to do the next question because it is weirdly hard. But yeah, thanks for watching. Don't forget to like and subscribe.